So now it's an arena for Karel Šafařík, who will tell us about Alice experiment. So I will try to switch the presentation. And, well, sharing screen. And your presentation is... I hope so. Yeah. Okay, so it's yours.
So thank you for inviting me to give this talk. I believe I have not to introduce myself. I was already introduced. Even Joachim showed my photo. Rolf Hoyer and our president. So I was asked to speak. Now it's inversed, Slovak and Czech contribution. That was the choice of the organizers for this meeting. Here it's the least, not all people who helped me or the material from whom I used in preparation of this talk. So I would like to start how the heavy ions end up in the LHC. In fact, that was already at the beginning conceived not only as a proton-proton collider, but heavy ion collider as well. And the first sub-detector concepts, not really a detector, were presented in the Aachen workshop in 1990. I find 3 talks by Emanuele, Peter Zondereg and Hans Specht, different part of the detector. But then was in 92 Evian workshop near Geneva, where many people have been involved, and there were 3 talks about possible detection of heavy ions and LHC, the dedicated detector, which finally end up as ALICE, modified Delphi, which seemingly doesn't work, and there was a CMS presentation that they would do the full heavy ion program. As the birth of the ALICE experiment, one can take the letter of intent, which was one year after Atlas, that means 93, will be 30 years next year. And there were technical proposals submitted in 95, and ALICE was approved finally in 97. Here, this is an interesting picture. That's the proceedings of the Aachen workshop. At that time was still alive the idea to have both LEP and LHC inside the tunnel simultaneously, and even to do electron-proton collision, which then was abandoned. Okay, and here are the documents of ALICE. First, I will show the contribution to the ALICE detector in round 2 and round 1 and round 2. I have to say that, you know, the detector is alive all the time. It's not something which was built and then is used. It's all the time improved. So that's why I divided it into 2 parts. Here, however, I put the number of the participating scientists in the ALICE project in Slovakia and Czechia. Here are the four institutes from Slovakia, 1 Bratislava, and 3 institutions from Košice, which is in East Slovakia. The numbers are the total number on the publications. In the parentheses, it's the number of PhD students. The same for Czechia, 3 institutes from Prague with the number. The total is around 20, both in Slovakia and Czechia, in total 40. And the number of PhD students is 1/3 of that, okay, so 70. Okay. Now, this is the ALICE detector in 2011 when we started. I will not go through all the parts, but I will just point you the parts where Czech or Slovak physicists participated. First is this silicon inner tracking system, which is enlarged here. It's from the central point, from the interaction point, up to half a meter in radial distance. The second large detector, which is the main part of the ALICE, is a huge TPC, which is this detector here. It's 5 meter long and 5 meter diameter, approximately. And then Czech physicists also take part in this detector, which is a precise electromagnetic calorimeter called PHOS, photon spectrometer. So I will start from Slovak hardware contribution to this first ALICE. First, we did some electronics. It's the silicon pixel detector router for collecting of the data. So here is the board and was installed in the pit. The silicon pixel detector in ALICE is done from the two pieces, the sensor part and the electronics part, which are bonded. The size of this pixel is of the order of 1/10 of millimeter, 150 micron precisely. They are bonded together. That was technology which we developed for heavy ion experiments, still in the fixed target program at CERN. And then the detectors are placed around the beam pipe, and this part is electronic, which collects the data from that. So this was developed in Bratislava, which participating in installation running and the electronics in Košice institutions. There was some interesting part. In fact, this detector was the first detector which see the first particle in the LHC, which happens on this date, 2008, where there was test of injection from the ALICE side, which was then stopped by material, and we see the splash of the muons coming to the SPD. And then a few months later, there was the first beam coming through the ALICE, again test of the injection, coming up to 3 kilometers into the LHC pipe. And this is a very interesting date because this was then celebrated, This was then celebrated in all the world because it happens approximately at 8 p.m. Beijing time. And that was the start of the Olympic Games. So, another large contribution on Slovakia was TPCS. I told you that large detector. The large part of this readout chambers, which are multi-wire proportional chambers, in fact, these lower ones, so-called inner chambers, was fully built, binding and produced at Bratislava University. So 26 of this chamber was produced in Bratislava. Here you see the picture of the machines which were doing that. And here is the installation on the surface near the access point to ALICE experiment. Slovakia also contributed Košice institution to the central trigger processor. Here's the example of the electronics board. I think it's a timing and control interface board. A large part of the Slovak contribution was a detector control system, which in the old time on the previous experiment was usually called slow control. Now in ALICE it's called therefore Slovak control. Okay, so it's the nickname of this. So they were participating in designing, development, running of the computer farm, and definition of the procedure during the data taking. So here are some pictures of that. Let me go to the Czech contribution. There was a very nice contribution to the development of silicon drift detectors. So first are pixel detectors, after there are drift detectors in this inner tracking system. They design and produce prototypes. Now, probably you don't know who this person is, so I have to tell you, he is Wojtek Petráček, now rector of the Czech Technical University, at the time where he has still hairs. Now you will not recognize him. Okay, and here is the test of this prototype detectors. To this detector, silicon drift detectors, was also developed low voltage power supplies. Here are the schematic, and here you can see the resulting prototype produced in Czech Republic. And the further, I think the last contribution in this part, the Institute of Physics was involved in the design and production of the crystal prototypes for this very precise photon spectrometer. It's very similar to the CMS, electromagnetic calorimeter, and then was designed and produced in Czech Republic this cradle, which is hanging the detector underneath the Alice detector. So then I will move to the contribution to the upgrade, which happened between round 2 and round 3. Again, the Slovak contribution, we had to change these readout chambers on the TPC because the TPC went to the continuous running mode, and there is need to change the readout chambers. So that's why we went from the multivariate proportional chambers to so-called GEM chambers. Here is the principle: it's 3 plates of GEM chambers, and to that there was need to investigate new gases, measure the drift velocities, discharges, etc. And this R&D program was done again by the Bratislava University. Here are the pictures of a small TPC when they measured the drift velocity laser to know when they originated the drift inside the chamber and the measurement of discharges. So this was a huge program of R&D to choose the gas filling for this new TPC readout chambers. Again, the Košice institutes participated in the upgrade of central trigger processor. I showed you before the boards. They developed another cards, cables, tested and debugged the new L0 trigger board. DCS was also upgraded, this Slovak control. There was a new development for the so-called archive managers of DCS. These are the two names. We completely rebuilt the inner tracker system, so it's completely pixelized and new. So the completely new data control system has to be developed. Trigger data quality monitor, etc. So there are pieces of software which were done which were the Slovak contribution. Czech institute, namely Nuclear Physics Institute in Czech, participated in the development of this new pixel sensor, which are now monolithic, and the full ITS is built out of 7 layers of those. And they contributed to the radiation hardness measurement. So in Czech, in the laboratory, they have a cyclotron, and this is the measurement setup. Sensors characterization, quality assurance system, and detector commissioning. Here are some results from that that software development. Very large contribution to this new, already coming into running pieces of ALICE is forward diffractive detector, developed at Technical University. It's a completely new detector and completely built in Prague, which the aim is to select diffractive events. What is diffractive already Sasha told you. Participate in the trigger and acts as the luminometer. So here it's done from the pieces of plastic scintillators, and the signal is taken by wavelength shifters by the optical fibers to the PMTs. There is still magnetic field, so we have to go a little bit outside. So here are the pictures of the building of that. Here is the installation of this detector. Dates. It consists of two pieces. It's on both sides, side C and side A, the installation. Here are the first measurement. For example, here it's measurement of the vertex using the timing of the FDD, so we can reconstruct the Z position of the vertex with this. And further, Czech contribution was MFT. It's muon forward tracker. It's again with the same silicon monolithic detector. We built a precise tracker which is put in front of the absorber. The muon system is only on one side, but in front, and there was no tracking in front of it. So now there will be precise tracking, and we can match the muons after the absorber and the track before the absorber, which will give you much more precise mass resolution. Will be then you can measure the single muons to study the heavy flavor production, etc. So this is already in the place. Here are the pictures from the installation, and again, our people participated in the development of quality control. Computing was already said, everything, just a few pictures. As was said, in Slovakia, there is tier 2 coupons composed of two farms in Bratislava and Košice. Czechia, there is also tier 2 center farms in Institute of Physics and Nuclear Physics Institute. Here it's on the map, connected. In Czech Republic exists much larger computing center in Ostrava, but that's used only, as far as I know, by Atlas, not by ALICE. Just to show, this is the cumulative distribution of number of jobs, so it's running smoothly. This is non-cumulative, just per unit of time. That was from Slovakia, that is from Czechia, running smoothly. And finally, I will give you some physics highlights. I will not tell you much things because there are too many. One of the interesting things which was done in ALICE was the measurement of antiproton to proton ratio in central region at mid rapidity. Why one would like to do that? Usually it's assumed that if you collide proton-proton or heavy ions, all the baryon number goes forward on one side and the other side. And if it's like that, that means in the center, the number of protons and antiprotons would be equal. So that we will have to obtain one. However, there exist different ideas that the baryon number is not transferred only by quarks, but can be transferred by something which is called string junction, which is a configuration of gluon fields. And if you take it perturbatively, gluon transfer in rapidity is not suppressed at all. So purely in perturbative QCD, you will get a part of the transfer of the baryon number not suppressed by the rapidity gap. At LHC, the rapidity gap is 9 units of rapidity, so it's the best place to measure it. And if you see significantly different antiproton to proton ratio, significantly different from 1, that means you transfer somehow the baryon number from the end by 9 units of rapidity to the middle. Now, it depends if one can use perturbative QCD for such soft project. What is the trajectory intercept of such a project, etc. So that's why it was very interesting to measure it. So here is the first measurement, goes nearly to 1. And here are the measurements for different combination heavy ions and different baryon, anti-baryon up to the anti-omega, omega. So it was very interesting, very cited publications. Was done, which is also nice, by student, at that time student Michal Broš from Bratislava, who is now in Prague, with a Czech-Slovak collaboration. This heavy ion study was continued by Michal Mereš from Bratislava. So that's one interesting. Second interesting thing, which was published in Nature Physics, was just a study. You heard something about the strangeness enhancement in the heavy ion. So the question was, is this a step effect when you go to the heavy ion collision? Is just depending on the number of particles you enlarge, and it's a continuous development. So it seems it's really a continuous development. Here is that ratio of this strangeness particle to pions plotted as a function of the charged particle density, and you don't see any effect. So this is a main analysis topic in Košice Institute. Another interesting observation was the measurement of ultra-peripheral collisions. This is done mainly in Prague by the group of Guillermo Contreras, who was also the convener of that group for a long time and member of physics board. So they measure cross-section of such interaction of the gamma with the nucleus. And these measurements, this cross-section, give you information about the shadowing. Shadowing is something that you change the distribution of the quark inside the nucleus when compared to the proton. And that's certainly observed. And saturation phenomenon, which tells you that at very small x, when the subconstituent of proton, mainly gluons, have very small momentum, they will saturate the function and they will not grow. So that's not observed. This is a cross-section with respect to energy of gamma, of the energy of the gamma nucleus and gamma proton interaction. You see the saturation will be this is not. And this point, there were different prediction, gives you the shadowing effect. It's somewhere in the middle of was the first measurement of this type. And the last, which I will show you, which I especially like it, the heavy flavor production. We measured the D mesons, and one of the interesting things we want to measure is the azimuthal distribution of those, if there is some preferred direction with respect to the impact parameter. That means the line between if you collide two nucleus, they are not head-on, they are semi-peripheral, peripheral. So with respect to that, you can measure the azimuthal distribution, which is then depicted as a Fourier coefficient, the V2, and it tells you will expect that the D mesons are produced in the hard collision, so they will not have a preferred direction. They just produce and don't see all this mess of the quark-gluon plasma, how people look at. What we observed, that is practically the same azimuthal asymmetry as the other particles. That means they somehow interact with all that matter which is inside. It's a very interesting result and needs to be still understood. Last slide, future. We had two future projects. One I think is already approved, is ITS-3 project, which we would like to continue with this development of the inner tracking system. We found out that we can bend the pixel sensors, they are now monolithic, and by bending them, we can copy a beam pipe. That means we can put it very close to the beam pipe. If you put it closer and closer, you would have better and better resolution for the vertexing. So this idea is really to go to the extreme performance in the detection of the heavy flavors, which decay close to the interaction point, and that's why you can get better resolution. This is already started. Nuclear Physics Institute already actively participates in this. And we just submitted recently a letter of intent for ALICE 3 project. These have nothing to do together. ALICE 3 will have ITS 4, as I said. Okay, so we continue like that. ITS is a little bit diverted from this numbering scheme. So this is a completely new detector, nothing to do with normal eyes. Will be fully pixel tracking, small solenoid, maybe even dipoles at the end, will be put inside but will not use the field of RC magnet. So it's a completely new project. We had just less than months ago a ALICE upgrade week in Prague. In fact, we have before ALICE Physics Week here. In fact, we have the last before COVID and the first after COVID here. Here are the pictures. And so we hope to continue in this development. Thank you very much.